last time we started this proof by showing that if graph isomorphism is NP hard, assuming that polynomial hierarchy will collapse to sigma 2, second level. So suppose that happens, suppose GI is NP hard, then GNI is co-NP hard, right? And how we will use this is we will convert the for all quantifier to there exist. Okay, that is what will lead to a collapse. But there is a complication. The complication is that we have shown GNI to be in BP.NP. Okay, so we have not shown it in NP. We have only shown it in randomized version of NP. So that is why this will be more complicated than the basic idea. So let's start with the sigma 2 sat instance psi. So there exists for all on phi, and we'll convert this for all y to GNI because we assumed it to be co-NP hard. So any instance of tautology can be converted to GNI. So this becomes psi becomes then there exists G, right, where G is a graph non-isomorphism instance. And now let us use that GNI is in BP.NP. So G essentially can be replaced by there exist over polynomial time Turing machine in a way. Formally what we will get is we will get the most operator, most MR, comma there exists A, and then a polynomial time Turing machine T which is acting on the GNI instance G, R and A, right. So we are reducing G to there exist, but then there is also this most quantifier because it's a randomized reduction to SAT. So overall we have reached an equivalent formulation of psi in terms of there exist, most and there exist over polynomial time computation. What is most? So most is as the name suggests, for 2/3 of the strings R's, this A will exist which will make T satisfy G comma R comma A. Now if we can flip X and R, there exists most, if we can flip it, then we will make progress because most can be replaced by using BPP in pi 2, most can be replaced by for all there exist. So then psi would truly become a pi 2 instance. Okay, so we would have reduced sigma 2 to pi 2 and hence sigma 2 pi 2 will be the same and pH will collapse. So our goal is now to swap there exist with for most, and so we drew this table or this matrix where the columns are X's and rows are R's, and one thing we can say immediately is that if this is true, if there is an X such that for most R the thing in square bracket is true, then we can deduce also this, right. Then in particular it means that for most R there is an X which is the same X as promised in the hypothesis. This also holds, right. So when psi is true, then the flipped thing is also true, but what if psi is false? Then we have to show that the flip thing is also false, and this is where we have to work more. So false means that for all x, let me bring the formula back. So psi is false means that for all x most r there exists A is false. For all x most r there exists T this is false, right? So no matter which x you pick, I mean assuming that psi is false, no matter which x you pick, most of the r's will reject, and rejection means that no matter which a you pick, T will be false for most of the r's. So this is what you start with, and we want to flip the positions of x and r, right? So the idea here will be to flip x and r's position let's use probability amplification. So let's define that is most r we define as probability over r 0 1 to the m of the event happening is more than 1 by 2 raised to 2n. Sorry. minus 1 by 2 raised to 2n. Okay, so in other words, the error we want to be we want it to be exponentially small, and to be precise 2 raised to 2n. So that is what now most means. It doesn't mean 1/3 error, but exponentially smaller error. Okay, let's start with that definition of most. So we have redefined the most operator. And with this redefinition, now you can see that if for all x, for most r's, something is happening, right? Then it means that the number of bad cells in the diagram is, so go over all x, so number of x's is 2 raised to n, and for each x how many r's can be bad? So that is 2 raised to m minus 2n, right, which is equal to 2 raised to m minus n. So this is again this is number of x's and this is 2 raised to m minus 2n is the number of r's. For nx. right. So, overall the BAT cells in this diagram are 2 raised to m minus n, and which means that, which means that for most R's, for most R's, for all x, negation of that happens. So, where here the definition of most is um, 1 minus 1 over 2 raised to n. Okay, so with this as definition, we can see that we can swap, because so the idea here has been that number of x's is fixed, which is 2 raised to n, but the number of r's is much more. It's m has been picked this works because we use m much larger than n, where n is the size of x. So, with respect to that, we can take bigger and bigger r's, and so then with that we can actually swap these two operators. So, what we have shown, hence we show that thus psi equals most R there exist x, there exist a t equal to 1, in both the cases. Okay, so when psi is true, in that case most R there exist x, there exist a t equal to 1 is true, and when psi is false, then also we showed that for most R, for all x, this statement there exists t is false. So, hence most R there exist a t is false. Okay. So, psi true, this thing is true, psi false, this statement is false, and hence these two are equivalent. So, psi has become equivalent to most R there exist a, there exists x, there exists a, and t equal to 1. So, Gx Ra equal to 1. Okay. So, we have come to this point, and now all that remains is to replace most by there exist for all quantifiers, and that we call step 4. So, in step 4 we use in pi 2 proof to replace the most quantifier by for all there exist. simply by for all there exist quantification. Okay, so this would mean that we put psi equivalent to, or in this form, for all some string S1, then there exists S2, then you have there exists X, there exists A, and inside you have the polynomial time, deterministic polynomial time Turing machine T prime prime S1, S2, X and A equal to 1. And what is this? So this is exactly the form of for all there exist, right? We started with psi, which was in which was there exist for all, and we have converted it after so many steps to for all there exist. So this implies that psi is now psi reduces to pi 2 sat in polytime, and which means that actually sigma 2 sat is in pi 2. Which means that sigma 2 is contained in pi 2. Which means that actually sigma 2, pi 2 and pH, they are all the same. Okay, so this leads to a collapse of the polynomial hierarchy to the second level. So that finishes the proof that graph isomorphism is unlikely to be very hard. So this is a useful technique for many other problems. And especially isomorphism problems. So it provides theoretical evidence to non-hardness. Of the non-hardness of a problem. But doesn't give an algorithm. Right, so it provides some evidence that the problem is not hard, like in this case GI is not hard, but it doesn't really give an algorithm. It doesn't tell you how to solve this problem. It just says that most probably it is, unlikely it is, I mean it is highly unlikely that the problem is NP hard. So with this we will now start a new topic. We are towards the end of the course, and we will do cover some models which are stronger than Turing machines. Okay. So going beyond Turing machines. So Turing machines capture problems that can be solved by one algorithm. And one algorithm for all n. Right? The algorithm doesn't really change uh, as n tends to infinity. It remains the same algorithm, just the input instances are increasing. So what if we allow different algorithms for different n? Okay, so essentially as n tends to infinity, you are using infinitely different algorithms. Now that seems that, as you will see, that this becomes very complicated. This is a very powerful model, because there is no uniform algorithm for all the inputs. Actually, with the changing lengths, the algorithm can be drastically different. There will be no correlation between two uh, different length algorithms, and then it may not be implementable in practice, because we are not saying what is the connection between n and the nth algorithm. It may be very hard to actually come up with that implementation. Okay, so this will mainly be a theoretical study, but one that will give you useful insights in a whole area. So there is an elegant way to model this. To model this type of computation, which is inspired by the real world silicon circuits. Okay, so circuits which you use in electrical engineering, in electronics, using them we can actually model this algorithm dependence on n, and have the possibility of having infinitely many algorithms for the same problem. So let's define. So this will use Boolean gates. So OR and NOT. Right, this is what a circuit uses. So we will use them in the definition and make it formal, make it mathematical. So we call it a Boolean circuit. So a Boolean circuit C on n variables this is a rooted tree with Boolean inputs x1 to xn at the leaves. OR and not. These are the three types of gates. In the internal nodes of the tree. And finally, output. At the root. Okay, so we have defined input output and we have defined the gates in the internal nodes, and it's a rooted tree. It's a tree structure. Computation flows from leaves to the root clearly. So let's see an example. So the XOR operation on two variables does what? It's basically addition mod 2, right? So if both are 1, it's 0. If both are 0, it's 0. Otherwise, it's 1. So x1 and x2 bar, or x1 bar or x2. That's the XOR function. And we can draw it as follows. So at the top you have an OR gate, right, and then OR gate has inputs AND gates. And these AND gates, the first AND gate has x1, x2 bar. x1, x2, and here you have like this, right? So x1, x2 bar and then x1 bar, x2 and then the OR, and that gives you the XOR output. So this is being we say that this is being computed by circuit C, right? So circuit picture looks like this. As promised, it's a tree, internal nodes, leaves, root, input, output, and three kinds of gates. And it's possible that, I mean, if you are computing a function, then there will be many output gates because each one gives you a bit. So for string outputs, we need many outputs or roots. So for decision problems, there is single output. For string output, for functions, functional problems, you need many bits to output, so there will be many roots in this tree. Okay, so this way you immediately see that every function has a Boolean circuit. Okay, so this is a complete model, meaning that every function can be computed by can be written as a Boolean circuit. Let's define few more parameters that are needed. What are the resources of a circuit? So the resources, the first is fan-in. So fan-in is the number of so just like Turing machines have time and space or non-deterministic bits or random bits, what are the resources in a circuit? So the resource parameters are first is fan-in, which is the number of inputs to a gate. Second is fan out. This is the number of outputs of a gate. And most important is size. So size is the graph size. So it's the number of vertices plus number of edges in the tree. And finally, depth. So this is the length of a path. From a leaf to the root. Right, so we'll be using these parameters, these resources for a Boolean circuit. So fan-in, fan-out, size and depth. So now we can ask, now we can actually define complexity classes. Right, so based on this, based on size, but before that, let me write this simple observation that for any function on n bits, for any Boolean function on n bits, the size for the circuit that represents or computes Fn, this is only 2 raised to n times n, right. So the proof is just by going over the basically the all possible inputs. So the number of inputs is 2 raised to n, so you can just go over all these inputs and whatever is the answer that can be computed by and or not, right. So you can check that the size of the circuit will be at most 2 raised to n times n.